I wanted to start this video by talking about what an electrostatic loudspeaker is and the differences between a conventional electromagnetic loudspeaker and an electrostatic loudspeaker. So if you look on the left hand side picture here, you can see a conventional electromagnetic loudspeaker. This is the cone you typically see on the outside. Attached to that is a coil or a voice coil, and that's protected by a dust cap here that you normally see in the centre, and then that voice coil sits within an air gap in a magnet. So as you put signal into that coil, you create an electromagnetic field, and that interacts with the magnetic field produced by the permanent magnet, and that interaction causes attraction and repulsion, and that's why you see the cone moving. In an electrostatic speaker, very different physics are at play. What you do is you charge a central membrane up, which is this, with a power supply. In the case of my speakers, we're talking about a power supply at 5 kilovolts. And then you have some grids either side, and in these grids you put high voltage audio. So that's created by putting a power amp through a transformer, stepping up the voltage. And you can see in this particular case we've got a situation where the signal is positive on this side, so it's positive going into this plate, negative in this plate, and the film is charged up negatively, and that film is attracted to the positive plate. So the question is, why would you choose an electrostatic loudspeaker over an electromagnetic loudspeaker? Well, there are a number of reasons. The first is you can see this film doesn't need any structural strength, doesn't need any stiffness, because it's driven over its entire surface. Whereas in a conventional cone loudspeaker, you're only driving from the centre of that cone. And so you need to design the cone, which is one of the reasons why it's a cone, to be very stiff, so that when you force it from the centre, you ideally get a piston-like performance. That's not required on here, so you can make the membrane very, very light. It won't break up at certain frequencies because it's being driven evenly over its surface, whereas a conventional speaker has to be relatively heavy to be stiff, and at certain frequencies you can have it where the cone is breaking up and you don't get a true piston-like performance. So that means the electrostatic loudspeaker typically is lower distortion, has better transients, whereas the electromagnetic loudspeaker can be much higher distortion. One of the challenges of loudspeaker design is what do you do with the radiation that comes off the back of the loudspeaker. So in the case of this speaker here, you can see that this membrane is moving in space. You've got a perforated plate on the front and on the back, and as much sound comes off the front as does the back, and at certain frequencies that cancels out, particularly at lower frequencies. You have the same problem with a conventional loudspeaker. The cone, if it was just sat in free space, particularly at lower frequencies, essentially would cancel itself out. Typically what's done with an electromagnetic loudspeaker is this cone is put within a box. The sort of rear radiation of the speaker is trapped and contained, and all you hear is the front radiation. Now there are some tricks you can play there, I won't go into that, to improve the range of that design. Typically what you see with an electrostatic loudspeaker is that both the front and the back are open. One of the reasons that you can do this with an electrostatic loudspeaker is you can make this membrane area very large, whereas typically you're limited by cone breakup on the electromagnetic loudspeaker. So making this area very large means it's less likely to cancel out at lower frequencies. The larger you make it, the lower you can go down without the speaker essentially cancelling itself out. Whereas you can't achieve the right frontal area to achieve that with an electromagnetic loudspeaker typically, unless you put it in a baffle. The typical dipole design of an electrostatic loudspeaker has lots of advantages and also disadvantages. It's a very natural sounding thing. You don't have the box tones fed off. It sits within the room more naturally, but can also be more difficult to place. and also typically if you want to achieve low frequencies with them, they tend to be very large. The speaker that I've designed is, well, I'm calling it a full range loudspeaker. It's down to about 100 Hertz, and you can see when we see the actual speaker panels themselves that they are very large. Whereas you can make a much more compact bass radiating unit with an electromagnetic loudspeaker within an enclosure. I mean, it's not impossible to put an electrostatic loudspeaker within an enclosure, but you do lose some of the benefits of the design. 20 years ago or so, I built a pair of electrostatic loudspeakers as part of my A-level project. The last few years they've not been performing particularly well. I think they've had a lot of thunder mites in them, which are small harvest mites that we get locally here, and because there's some quite high voltages in them, that tends to make them arc over and not perform very well. So I've taken the opportunity to take them apart and rebuild them. This is the panel outside of its frame, and I've taken this panel apart and just want to show you how they work. So you can see it's about 1800mm long, about 300mm wide, so it's a big loudspeaker, but it's only about 50mm thick. If I take this apart, so I've undone the screws that fasten this thing together. Hopefully that will rest there. So you can see that this is held together with a load of nylon studs that I take it out. I'll actually be changing that in the next design. But what you can see here is the perforated plates, the insulators between the perforated plates, and then this membrane. And this membrane is made up of very thin mylar with a coat of graphite on it, and you can see these copper strips are what essentially allow the electricity to feed into the membrane and charge the membrane up. And then on the other side we have these insulators and then some plates. So the gap between the perforated plates where the audio signal comes in and the membrane is about 3mm. You also notice that we've got two sections of speaker here. This thin one here is the tweeter, and this wide one here is the woofer. And the reason that there are two separate speakers is to try and disperse the sound more effectively across the audio range. If you have a wide speaker like this that does the full range, what you find is that at high frequencies the sound beams, and so it can be a very harsh sound in your room. You'll notice that, say, speakers like Martin Logan's, they have a curved membrane. That's to achieve the same effect. The old style quads had a very similar system to this, where they had a thin tweeter and a wide woofer. The later quads use a kind of phased array to give an effect of a sound field. So these are all methods to allow the sound to disperse more naturally within the room, rather than being a beamed sound. Conversely, these are very, very long, so they're what are called line source, which means at most frequencies the sound doesn't disperse vertically, and this can offer some advantages in terms of how the system sounds, in terms of acceptance of positioning within the room, and a number of high-end speakers that you'll see, even cone type speakers, are line source, i.e. they have multiple tweeters in a row to give that non-dispersal effect vertically. While I'm rebuilding these, I'm going to take the opportunity to make some improvements. As I mentioned earlier, these speakers were held together with nylon studs, something that looked a little bit like this, and those were threaded into this side, went through this side, and then there was a nut that clamped the two parts together. I did that because I wanted to be able to get into the speakers, because I wasn't confident about the design. Obviously 20 years has passed, I'm happy with the design fundamentally, so what I'm going to do now is bond all the layers together. That's got two advantages really. There was an issue here with the rods going through, even though they're insulating. There was still potentially, in some high humidity situations, corona discharge through the air gap there, which was not good. The other disadvantage is there are bits of panel that are pushing against each other but are not firmly fixed. So if you've got a resonant frequency, then you could potentially see some interaction, some buzzing from those. That didn't really happen, but yeah, it's something to try and avoid. So that's the first change. The second change is you can get thinner mylar now. So I will be making these speakers with thinner mylar. So probably about a quarter of the thickness of this, just a few microns thick. And that hopefully will improve the sound, improve the transients, potentially improve the high frequency performance as well. And the third change is you can see these insulators here were made of strips, and there were gaps in between them. Again, this wasn't great from a kind of corona discharge point of view. In some conditions, there was some discharge down through these gaps, which resulted in a sort of a high frequency hiss. So the new speaker design will be made of one solid sheet. It will have radius corners here and be much better from a high voltage perspective. So my job now is to strip these panels down. The only part I'll be reusing is these perforated plates, which I'll strip of all the varnish, the high voltage varnish off them, clean them up, and we'll reuse those. As I said, the mylar is being replaced. I'm going to have different insulators. The whole design is supported on 2 MDF panels with cutouts. I'll be remaking those as well to do a neater job than I did 20 years ago. Here you can see 2 of the old frames, so this is one from the front and the back. This one's still got its grill cloth on, and you can see where the perforated plates were glued onto these MDF frames. So they're a bit rough, and I'm going to improve these in the second iteration. These are the steel speaker frames I built 20 years ago, and I'm going to reuse those in the rebuild. On the back of the speaker are 2 electrical boxes. This one's the high voltage power supply, and this one's for the audio transformers. With the electrical boxes open, we can see the audio transformer for the tweeter and the much larger audio transformer for the woofer. This is larger because of the low frequencies and to avoid core saturation. In the high voltage power supply box, we have the mains connection, fuse and switch. We have a custom wound high voltage step up transformer. I had to custom wind this because trying to find one that did the voltages I wanted but was still compact was basically impossible. We then have a potentiometer to adjust the bias voltage and a voltage multiplying circuit. You'll also see there's an array of resistors here. There's a multi-meg ohm resistance between the power supply and the output here to the panel, and there's several reasons for that. The first is if someone happens to touch the high voltage side of the panel, then the current is very limited. The second is if the membrane touches the perforated plates, then it's much less spectacular than if you didn't have that resistor. And the third one is this increases the charge time of the membrane, which due to some boring science means that the force on the membrane is more linear as it approaches the perforated plates, and so it gives lower distortion to the audio signal or audio sound that comes off. The panels have been removed from the old speakers, paint removed from them, cleaned up, and now they've been sprayed black. And then on the inside faces, or the faces that face the mylar, they'll have some high voltage varnish insulation on them. the membrane's been tensioned up on the table, and now we've taken the double-sided tape off the speaker and rested the speaker, or the speaker half, on the membrane. So now the speaker should be stuck to the membrane. So this is the speaker with the film tensioned and the conductive coating applied. You can see it's starting to dry off at this end. So this is one of the speakers assembled without the grill cloth on. I thought I'd film this because it looks quite cool without the grill cloth on. Unfortunately, I think it's probably better to have some protection for people poking their fingers in it, and also for dust and harvest mites and things getting in. The grill cloth offers some protection for that.
Here to share, I'd rather we get him a good grey mare. He kissed a good wife and struck a good man. That's the tricks I call a tam. Tam.
So you've seen the speakers or heard the speakers working, and I thought I'd give you just a quick tour of the rest of the system. So in here on the right hand side we have a CD player and a tuner. That then feeds into the Quad 44 preamp, and the output from the preamp goes into a silver box there. You can't really see very well, but that's an active crossover, and that's a three-way active crossover, analog active crossover. The treble goes into the Quad 306 power amplifier. The mid bass goes into the Quad 405, and the bass goes to some active subwoofers. So if you come over, we have the electrostatic speaker that you've seen, and then located on the back of the speaker is the subwoofer, and that's motional feedback subwoofer, active subwoofer. It's got two voice coils on the cone. One powers the cone, the other monitors the position of the cone, and there's a feedback circuit in there to correct overshoot or distortion. So the tweeter, electrostatic tweeter, crosses over to the mid bass at about 1 kHz, and the mid bass crosses over to the subwoofer at about 100 Hz.